Alright, hello everyone, my name is Jeff DeBose, and today I'll be talking about a project entitled TiO2-Assisted Halide Ion Segregation in Mixed Halide Perovskite Films. So as you probably know, perovskite solar cells utilize transport layers to extract charges, i.e. electrons and holes. And these, for example, the electron transport layer can be something like titanium dioxide, TiO2, and the hole transport layer can be something like spirometad. Now in the case of mixed halide perovskites, they can undergo light-induced phase segregation, which is deleterious to its optoelectronic properties and something that is generally something we want to avoid. Now, what this project is really trying to show is that the transport layers that we employ can actually influence phase segregation in mixed halide perovskites, specifically when there's a case of unbalanced charge transport. Okay, so now the methods for this project, we're basically going to use transient absorption spectroscopy, and it's going to do two things for us. One, that's going to induce phase segregation, so the 387 nanometer pump laser pulse is actually going to induce that photoinduced phase segregation. And second, we're going to basically track the formation of new phases, i.e. bromide-rich and iodide-rich phases, through the standard pump probe techniques of transient absorption, and that's going to be able to allow us to track whether or not phase segregation is happening and at what rate. So the basic idea, we have our mixed halide perovskite, and we're going to deposit it on several different substrates under different conditions. So the three conditions studied essentially are the mixed halide perovskite on zirconia, which is an insulator, mixed halide perovskite on TiO2 under degas conditions first, and then mixed halide perovskite on TiO2 under ambient conditions. And I'll talk about why the oxygen being present is important in a second. So if we flip over here to our results, so this is the transient absorption spectra of our mixed halide perovskite on zirconia. And as we can see, as we irradiate over time, we start with one bleach feature or excited state feature corresponding to the mixed halide perovskite, and over time that essentially just shifts a little bit and decreases, but we see no new growth of new phases like the bromide-rich or iodide-rich phase that we expect to see. If we look at the mixed halide perovskite on TiO2 under degas conditions, we see something very similar. We see one bleach feature corresponding to the mixed halide perovskite, and that does shift a little bit and decrease over time, but we see no new growth, new phases, therefore no phase segregation is occurring. Now when we have the mixed halide perovskite on TiO2 under conditions with oxygen present, we see something very radically different. We see the loss of our mixed phase over time, and the concomitant growth of a bromide-rich phase and an iodide-rich phase. So this is the only situation that we actually see the phase segregation occurring. So if we look back at our band alignment in each one of these cases, if we flip over here, so the mixed halide perovskite on zirconia, essentially because this is such a wide band gap insulator zirconia, we don't have any electron transfer, so electrons and holes can just recombine within the mixed halide perovskite. When we have the mixed halide perovskite on TiO2 under degas conditions, we can't have electron transfer into TiO2, but it can just essentially recombine with the mixed halide perovskite since it has no other pathway available to it. But when we have the mixed halide perovskite on TiO2 with oxygen present, we now have a situation where the electrons can be scavenged by oxygen and essentially leave the system, which leaves an accumulation of holes within the mixed halide perovskite. So we essentially posited, okay, there's something going on with these holes being accumulated. If it is happening to be the holes that are impacting and driving this phase segregation, we posited essentially, can we suppress the phase segregation by also extracting those holes? So the next thing that we looked at was, the mixed halide perovskite on TiO2 with oxygen, so a system where we can extract the electrons. We also deposited onto that spirometad as a hole transport layer. So now we have electrons being transported away in addition to holes, so we're avoiding that hole accumulation. And the results here, we can see, okay, a very similar result. So we're seeing only the little bit of a loss of the intensity from the mixed halide perovskite film over time, but no new growth of a bromide-rich phase or an iodide-rich phase. Therefore, we've suppressed the phase segregation by basically balancing the electron and the hole transport. So the sort of the main conclusions from this project is that we ended up seeing phase segregation in mixed halide perovskites only under conditions where we have hole accumulation. And the phase segregation is able to be suppressed when those holes are extracted through the addition of our spirometad hole transport layer. So this project sort of shows the importance of balanced charge transport, which is crucial for maintaining the stability of these mixed halide perovskite films and their optoelectronic properties. Thank you.